All right, guys, I hope these videos are helpful for you. Here's 8.2 notes, page 4. A simple random sample of 1,460 is obtained from a population size of 25,000 with a population proportion of 0.82. Describe the sampling distribution of that. Well, we're trying to figure out if this is normal or not normal. If it's normal, we can proceed and do the calculations. But if it's not normal, we don't want to proceed. So I like testing this first one, n divided by n. And if that number is less than or equal to 0.05, then we can continue to the next test. This test is the easier of the two, so I'm going to shove that in there. 1460 divided by 25,000. Whoopsies. 1460 divided by 25,000. Too big. 0.0584. 0.0584. 0.0584. It's too big. So we just say this one's not normal. Reminds me of a girl I dated in college. Next, a simple, we don't even have to go further. It failed the first of the two criteria, so we stopped. Next, this time we're choosing from 1.5 million. Same scenario. So cross your fingers. If this is not less than or equal to 0.05, we get to stop. So when we shove in 1460 and 1.5 million, that's smaller. 0.00097. So the first criteria is checked. Now let's check that second criteria. That second criteria that must be made is that this NP, the variance, times 1 minus P, has to be greater than or equal to 10. If it's greater than or equal to 10, and it already passed that first criteria, we're going to describe this sampling as being normal. So 0.82. Oops, I did it out of order, but luckily multiplication is commutative. 1460 times 1 minus 0.82, was that 0.18? 215 is 215. Greater than or equal to 10? Yes. Check, check. So this one is normal. So we can go on to the rest of the problems. Okay? The rest of these problems are going to ask questions about in between, up above, down below. So the two values that we need to compute are the average for this binomial sampling. That's just that. Okay? It's a percentage. We know that this, for the binomial sampling, is going to be a number trapped in between 0 and 1. And then for the standard deviation, it is the square root of all of this garbage. P, 1 minus P, all over n. Little n, that is. So 0.82, 0.18, all over tiny little n. Take the square root of that stuff, and you get 0.0101. So that is the standard deviation that we're going to use in our problem. Those are our two values, and here we go. These problems have a slight twist to them. Let's draw a picture. So what's the probability of it obtaining between 1190 and 1220 individuals? Well, this is individuals, but our average is not individuals. Our average is the percent of individuals. So we're going to either have to convert that to individuals, or we're going to have to convert these to percents of individuals. So we're going to convert these to percents of individuals so that we can use the proper standard deviation. Okay, so what is the percent of individuals in our sample here that are between this and that? We compare that to 1460, and we get the percent for that. .815. And the percent for the upper bound, that's the number of individuals. The percent of individuals in our sample is you guys are a lot faster than I am at this. 0.836. A picture of this event looks like this. We've established that this curve is normally distributed. We put the average smack dab in the middle, 50% to the left and 50% to the right. And where's this? 0.815 is down here somewhere. 0.836, that's up here somewhere. We want the area in between. I hope you guys understand this sample. Again, when you use a percentage or a probability for the average, then your comparisons have to be the same too. All right, here we go. We want the normal CDF, shift data distribution, normal CDF. What was the average? 0.82. What's the standard deviation? 0.0101. What's the lower bound? 0.815. What is the upper bound? 0.836. Calculate that. 63% are going to be in that zone, 63%. Since that 63% is greater than 5%, then we say this is not unusual. Moving on. The probability of obtaining 1,180 or fewer individuals. So here we go. 1,180, that's the number of individuals, but our average is based on the probability. So we need to convert individuals into probability. What percent of the population that I tested, what percent of our sample? 80.8%. Okay, let's take a look. We put the average smack dab at the middle, and 0.8082, that's to the left of that average, and we want that or fewer means shade to the left. So we want to the left of that value right there. Time to plug it into our calculators. Shift data, distribution, normal CDF. 0.82, 0.0, that's nice. The lower bound this time is negative infinity, but the upper bound is 0.8082. Hit it. 12%. Again, that's still bigger. That's still bigger than our value of 5. So this is not unusual. I'm looking at the prepared notes, and I noticed that it's slightly off there. I think they rounded, and I kept it out to a couple more decimal places than they did, so that's why we're off just by a touch. I hope that doesn't happen to you guys on Pearson. What's the probability of obtaining 1250 or more? Let me just draw the picture. You guys can set this up. $12.50 divided by $14.60. $8.562. That's over here somewhere. It's bigger. So 0.8562. Boom. So we want bigger than that. So we go into, I'll just finish her out. Normal CDF. The average and the standard deviation stay the same. This time the lower bound is our 0.8562. Upper bound, positive infinity. Let's calculate it. Scooch, 0.0169%. And that is unusual. Why? Because that number is smaller than 5%. And we are done with page 4.